28, was that? It wasn't 28 though, was it? Was it 20? Let's see, 24. What was the next one? Well, was that that was the last one, wasn't it? How about that? The time to spare. Well, we're not done though. You see, there's this problem here I wanted to show you. It's number 28 in your book. And it deals with tension in a cable. That's what's this one's a little bit different from that perspective. Plus, then you have to do a little bit more thinking to get your free body diagram solved. Okay? So what's our free body diagram? There's some other things involved in this one too that we're going to have to look at. What's our free body diagram going to look like? Well, how about like this? It's basically a beam on an angle, isn't it? So it's just a straight line. Bless you.
Thank you.
Now we've got A down here. We see is pinned, right? It's pinned on that angled surface, but it's nonetheless it's still pinned. So we're going to have an AY and an AX. Now I'm going to guess that AX is going to the right here, and that's a pretty good guess. Because think about this. You've got this mass up here that's trying to push this bar or beam, whatever, down into the ground, isn't it? So wouldn't it be pushing, it's trying to push down and to the left, right? Because of all that weight on it. So I'm thinking it's going to be that my wall has to push back to the right and up to keep it static. Well, then we know we've got this mass out here, and they do give that as a mass, and they say, what do they tell us in that problem? Mass is 300 kilograms, right? Yep.
That mass will make the other end going up, or it goes whole body.
The mass is trying to push this thing back, if I can find it, trying to push it back down, isn't it?
But it is in angle, it is not vertical.
Doesn't matter if it's vertical or horizontal. The mass itself is pushing straight down, right? So you're telling me if I take this pin and put it over against the wall and I start pushing down, what's the wall and the floor have to do to it? I'm putting, whether I'm hanging that weight out there or I'm pushing, it's the same thing, right? So the wall has to push back.
If I push on this side, my calculator will put this part goes up.
But that's not what we're doing. It's pinned down here. It's not pinned up here. It's pinned down here. Now there's a cable out here that's going to keep that from going like this. Okay, but it's pinned right here. So if it were pinned where you said, yeah, it would be doing something totally different. But that's not the case. It's pinned here. Cable is just going to help hold it. Keep it from going like that. Okay? But we have to draw the rest of the free body diagram, and that'll make more sense maybe with that. So I've got that mass, which they said is
300 kilograms.
300. Thank you. Kilograms. And then you have to do something like times 9.81, what is it, meters per second squared? You know, I couldn't think of that until just now when I was doing this problem. It's like I know there's a unit for that, but I couldn't think of it, and it just hit me. 9.81 meters per second squared, so that you end up with a weight of 2.94 kilonewtons. Is it killi or kilo? Kilo, isn't it? Kilonewtons. Okay, so that's one of the little tricks you have to mess with. You have to change that to kilonewtons, right? Then we had the cable, and that cable is in tension.
Why are we
What?
not following with the 9.81?
Well, if you're given a mass, it has to be turned into a weight, right? If you're given mass, which is kilograms, you really need to have it changed over into kilonewtons.
That is 9.8 meter per second square.
Yeah. And since it's kilograms, it would have to be 9.81. If it were pounds, it would be something like 32 point something, isn't it? Yeah. Because they're saying it's a mass, you have to get that turned into a W. And weight is mass times acceleration.
mg.
If we see something like that on the quiz, would you give us the
Absolutely.
factor?
Absolutely. The conversion. But there again, if you see that on a test and it's an open book, you've got the conversion table in front of your book. Right.
0.4536
Do what?
From pounds to kilograms, I guess.
No, we wouldn't do pounds to
You
kilogram.
want to go the other way.
You just want to do, no.
Oh,
no.
you were saying the 32.
If you were, yeah,
Yeah.
it would be 32 point something. I can't remember exactly what the number is. And I don't expect you to. That's what you got the book for. Okay? Okay, so now we're going to label this as the tension in, and I call it BD. I just go with the alphabet there on that. Okay, that's all we need to call that. It's the tension in the cable BD or DB, however you want to look at it. I don't care. Okay, and that's all we need for our free body diagram. Well, that's not all we need, but that's what the free body diagram looks like. We're going to need some distances too, aren't we? We're going to need a distance specifically. We're going to need a distance for this right here. Now I'm going to just down here beside that, I'm going to call that X. And then we're going to need a distance for here. And that's going to be my Y. That's all we'll need, right? You can figure out the other distances too, but that's really all we need right there.
No, that is Vx or what is that? In a video of
Here?
yes.
BD. The tension in BD. Okay? So, if we want to find that, what are we going to use? To find that X value, let's see now. Oh, and I guess I should have put this right here, shouldn't I? 60 degrees. To find the X value, isn't that the adjacent side? Okay, we know the hypotenuse, it's given, right? That's 3 feet. And let's see the way they did that. Yeah.
3 meters.
Oh, 3 meters, sorry. 2 meters. Yeah, that wouldn't be fair to have meters and feet screwed up there, would it? Since we're in kilograms, kilonewtons, that would be killer to have feet. I wouldn't do that to you. So, if we want the side adjacent, well, it's the adjacent over the hypotenuse is the cosine of 60, right? So would it be the adjacent would equal the hypotenuse times the cosine of 60. So this number right here, if you will, the adjacent is equal to, in this case, 3 meters times the cosine of 60. And that should be 1.5 meters. Well, if we need this Y value,
Shouldn't you be using
What?
5 instead of 3? You're trying to get to.
oh yeah. It's 5. I did both of them. And it ends up being 2.9, I think, isn't it? 5, which is the total, right? I'm looking for this x. I actually did x1 and x2 in the problem.
I was going to ask you how come we don't need x2, or how come you don't need the distance out
Well-
where point B hits the beam?
Right here?
Yeah.
Yeah, you just don't need that because there's not going to be any moment equation calculated from that. We only need this x value for the one that's going in the y direction, and we only need the y value for the one that's going in the x direction
Okay.
for the moment equation. And the rest of the sum of the forces in the x and sum of the forces in the y don't use any values anyway, do they? So that is actually 2.5. Sorry, that's, yeah, 2.5 meters. Thanks, Clark. Okay, then to get the other one, and that's the x value, right? To get the y value, we're going to go with the opposite over the hypotenuse is the sine. So the opposite equals, and I want to make sure I get this one right, that's going to be 3 times the sine of 60. And that value is 2.6 meters. Okay, so this one's 2.6. This one's 2.5.
Why wouldn't we use 5 again for the second one?
Because, see, we're only looking for this segment right here.
Oh, okay.
So our triangle looks something like this.
Okay.
Okay, so we only need this segment. So that's 3. Okay? Anything else? All right. So now we know enough. We've got all the information we really need for the free body diagram in this case, right? So now we can just go and do our sum of the forces in the x, sum of the forces in the y. And again, I know this sum of the forces in the x equals 0. I know I don't have enough to solve for this, but I go ahead and put it down. What do I have? I've got, in the forces in the x, I've got a negative tension in BD plus AX, right? 2 unknowns. So I don't even have 2 equations, so I can't even do substitution if I wanted to. So I just try to find something else out. So then I'd go do my sum of the forces in the y. I think actually I've got enough on that one to do something here. Well, let's see. I've got AY going up, right? Minus the 2.94, which was that weight that we're actually trying to support. 2.94 kilonewtons. Therefore, AY equals 2.94 kilonewtons, doesn't it? This negative, when you switch it to the other side of the equation, it becomes positive. So it's 2.94. We said it was going up. It is going up. Okay, so that kind of, you can see that right there, can't you? You got AY going up, you got 2.94 kilonewtons going down. AY has to equal 2.94. There's nothing else going on there. And you could actually say AX is going to have to equal the tension in that cable too, isn't it? Because those are the only 2 things that are acting in the X direction. But we still don't know what they are. So we'd have to go in there and do a sum of the moment at A. Yeah.
Can you just load this up and see that quick?
Do I now?
Can you scroll just a little bit up so I can see that? Wait.
So if we do the moment at A, we've got the tension in the cable, tension in BD, and that is multiplied by the distance, 2.6 meters. So what was going on there? How do I determine that that's positive? Well, look, if I'm looking at point A as my pivot point, BD, the tension in BD is trying to make that thing go counterclockwise, which is positive, right? And there's the distance of 2.6 relative to the point A. So that's where that came from. Then I've got the 2.94 that's actually pulling down on that whole system, isn't it? Which makes that thing want to spin clockwise. So it's a negative 2.94 kilonewtons. And the distance on that one is that X value, which was 2.5, wasn't it? Those are the only two things we know. So if we leave T, the tension in BD, where it's at, put this on the other side, it becomes a positive value. So it's 2.94 times 2.5 divided by 2.6. And you find out that the tension in that cable is 2.83 kilonewtons. And then if we're just calling out tension, we call out tension just by putting a T and circling it. And if it's compression, it'll be a C with a circle around. And then I would probably just put a box around that.
So you don't want an arrow on that?
No. No, it's just tension is because tension can be going any direction. Okay? And since it's a cable will always be in tension. So yeah.
That symbol
Do what?
in the exam.
I would like to see that symbol on there as opposed to the arrow. Yes. Because we have to start thinking tension and compression because we're going to be doing that in that next chapter.
So if it did come out negative 2.83, you'd be in compression then?
Yeah.
Yeah.
Yeah. But since it's a cable really can't ever be in compression.
Yeah, just if we did assume wrong for some reason.
Right.
Because we're not smart.
Right. It's not a matter of
I mean,
being.
not making
It's really not a
educated
matter
guess.
of being smart
Yeah.
or not. I mean, sometimes you really can't. That one case, we were only a half a whatever kip
Yeah.
from going the other direction. That can be a crapshoot, you know. So really, it's kind of an educated guess,
Yeah, that's what I mean.
you know.
How can we read that? Tension at BD is equal to 2.83 kilonewton circling.
With the circle, what about it? Yeah, that's how I would like to see it. The tension in the cable BD is 2.83 kilonewtons in tension. Okay? Well, now we can take that, substitute that back in up at the X equation. 2.83 was it? Yeah. 2.83. AX stays where it's at. The other stuff goes to the other side of the equation and you end up with 2.83 kilonewtons. We said AX was going to the right. It came out a positive value, so AX is going to the right, isn't it? And that's the reaction at A relative to the x-axis. But we're not done yet. See, because if you look in the problem, determine the tensile force in the cable and the reaction at A. Okay, well that's the reactions at AX and AY. But that really, I think what you really need there is what's going on in that. Let's go back up here. What's going on in this? What do you want to call it? A bar that's holding this up. Well, it's actually there's compression going on there, isn't there? Well, what's the compression turn out to be? Well, that's going to be, you're going to do this. You're going to go back to chapter, what, 2 maybe? Resultant vector is the square root of the x value, which is 2.83, right? Squared, plus the y component, which was 2.94 squared. And you find out that there's actually 4.08 kilonewtons, and it's really, it would be compression there. But then you also need to find out what the angle is. And remember the arctangent of what? 2.94, which is the y, right? Over the x. And that would be going off at 46.1 degrees. Seems kind of odd, doesn't it? But that's what it would be pushing. So your resultant force then at A would be 4.08 kilonewtons at 46.1 degrees in the first quadrant, if you will. That would be the rest of the answer. And that's problem 28. That's just, I wanted to show you that as an example. And here's what I would like for you to do for Friday. Do problem number 30. 46. 30, 46, 50, and 51. Shouldn't be too difficult. So then that's the game plan. We'll do those problems Friday, and then next Monday we'll have a quiz over very similar problems. Okay? I will. Do what? No. No, I want to do some more problems, and then we'll have our quiz on Monday. And I will post the videos up later this afternoon or this evening. Okay.
About how many questions